Okay, brand new chapter for us. Chapter 11, acids and bases. Some of this is stuff that we're doing this week. You don't actually have to have known it to do the lab practical or last week's lab, but it might help. So what are acids, what are bases? Acids are found in a lot of foods, like citric acid in lemons and limes, and probably grapefruits. Acetic acid is present in vinegar. Tartaric acid is one of the acids used to coat sour candy. There's a notable sour candy. It's not named here. I probably wouldn't get in trouble for it, but Sour Patch Kids. The way that acids work is they combine with saliva in your mouth and they produce H+ ions. What is H+? It's a hydrogen ion, hydrogen with one electron removed, which leaves a proton. So this is commonly why people, chemists, might say that protons are sour. Those H+ ions, those protons react with things on your tongue and send electrical signals to your brain that you experience as a sour taste. If you get them in your eyes, it doesn't send that sour taste to your brain because your eyes don't have taste buds. It just hurts. Some properties of acids include having that sour taste, like lemons and limes. They can also dissolve many but not all metals. And if you have blue litmus paper, it'll turn that red. If you've got the fancy litmus paper, it'll turn it a specific color depending on which litmus paper you have. Some common acids are things like hydrochloric acid, might show up in your toilet bowl cleaner. We've used this one before. Sulfuric acid, like we were using last week in Lab 11, shows up in car batteries. Other things like nitric acid we use for our copper lab to dissolve the copper. And some other examples of things further down there from our book online. So those are just some fun facts for you. Some properties of bases. Bases have a bitter taste instead of a sour taste. That bitter taste might be a warning that we shouldn't be eating them or drinking them, but sometimes we know better, and so we drink our coffee anyway. Bases also have a slippery feel. Bases are often used in the production of soap, where they combine bases with fats, and that produces the soapy molecules. On your hands, you've got oils on your hands, and so those bases will combine with the oils on your hands to produce a little bit of hand soap, soap made from your hand oils. And that's what produces that slippery feel, or what might produce that slippery feel. The opposite of acids, bases turn red litmus paper blue, so we're just changing the directions. We've used the red litmus paper before, or the blue litmus paper. We used one of them in one of our labs before. Bases show up in a bunch of products like Drano and tonic water. Bases are not as common as acids in foods. Alkaloids are a type of organic base that are often poisonous. Obviously, poisonous is bad. And that bitter taste may have been developed as a way of identifying that, hey, we shouldn't be eating this because it's bitter, and bitter things are often, like alkaloids, poisonous. But coffee has some bases in it, some bitter compounds in it, and so we drink it anyway. Some examples of bases include sodium hydroxide, which is often called lye, potassium hydroxide, a different type of lye, magnesium hydroxide that might be used in some antacids and deodorants, and there's some other fun things that you might read about there on your free time. Again, a table from our book. How do we define acids and bases? We've got this definition from Svante Arrhenius. The Arrhenius definition. You'll want to know the Arrhenius definition. For acids, this is that it produces H+ ions in aqueous solution. Right, aqueous solution meaning that water is our solvent or our majority component. HCl is an example of an arrhenius acid. It's a covalent compound. It doesn't contain ions. It doesn't consist of formula units. It contains as separate molecules. And when you add it to water, it separates into H plus and Cl minus. Since it forms H plus when you add it to water, that makes it an arrhenius acid. So the two important parts for our arrhenius acid: produces H plus ions in aqueous solution. If it's not in aqueous solution, if it's a different solution, it's not technically an arrhenius acid. Also, if it doesn't produce H plus, not an arrhenius acid. Those H plus ions are very reactive, and in aqueous solution, so if water is our main solution, then they'll bond to water. The oxygen says, hey, I can share some electrons with you, and it forms this H3O plus. H3O plus is also called the hydronium ion. If we've got H plus that's forming in water, those H plus ions are always going to latch onto a water molecule. They're everywhere, so they're just going to get snatched up immediately. We're never going to find them alone as H plus. We will often use these interchangeably. You should know if we're in aqueous solution, if we've got water around, it's actually H3O plus, but we might call it H plus or write H plus just to save a little tiny bit of time. Any questions so far? Great. When we are writing acids, this doesn't apply just to arrhenius. In this class, we write our ionizable hydrogens first. Ionizable here meaning it can form H plus, which immediately turns into H3O plus in water. So for example, formic acid, we have an H in the front. It's HCHO2. This is not how you'll see it everywhere, but in this class, that's the way you'll see it. This H in the front means that that one hydrogen can form an H plus. We also have this other hydrogen, the second one, and that one, because it's not in front, does not produce H plus. So that's one of our big hints. We talked about it when we went over nomenclature a couple months ago. The H in front means that we have an acid. The number of H's that we have in front is the number of H's that can pop off in water. In this case, we just have one. We can also look at the structural formula or the molecular formula. So the structural formula for formic acid is over here on the right, and it's this right hydrogen that's the one that will pop off. You don't really need to know that. It's just in case you were wondering, that's where it's located. So that's our Arrhenius definition for acids. For bases, our Arrhenius acid, or Arrhenius definition, is that it produces OH minus ions. And again, this is in aqueous solution. So for both of our definitions, they have to be in aqueous solution. Sodium hydroxide, NaOH, is an example of an Arrhenius base. When you add it into water, it separates out into sodium, Na+, and hydroxide, OH-. Just because we have an OH doesn't mean necessarily that it's going to dissociate. So a lot of alcohols, we might write like this one for methanol, CH3OH. That's the one you can't drink. That OH does not pop off and produce OH minus in solution. So again, the important parts for our Arrhenius definition for bases is it produces OH minus, and it produces that in aqueous solution, so if you add it to water. In our Arrhenius definition for acids and bases, the acids, which produce H+, and the bases, which produce OH minus, combine, and those form water. So the H+ from our acid, the OH minus from our base, form H2O water, which is good. That's all fine. It's true. However, some things behave like acids and bases even though they don't meet our Arrhenius definition. Even though they don't directly produce H+ or OH minus. So that's a shortcoming of our Arrhenius definition. It also doesn't apply to non-aqueous solvents. So if we're not using water as our solvent, the Arrhenius definition doesn't work. So I hope you didn't grow too attached to the Arrhenius definition, because the one that we're actually going to use most of the time, you should still know your Arrhenius definition. The one we'll use most of the time is our Bronsted-Lowry definition. And here's our definitions for an acid and a base in the Bronsted-Lowry framework. So our acid is a proton donor, a proton like an H+, and a base is a proton acceptor. So these two definitions are more broad. Notice that we're not specifying that we're in an aqueous solution, so this works outside of water. And we're not saying that our base produces OH minus, it's just something that accepts an H+. So we're primarily focused on the movement of our H+. Any questions so far? Cool. All right, so HCl we saw was earlier is an Arrhenius acid. It's also a Bronsted-Lowry acid. If we put it in an aqueous solution, we'll have water present. It's going to produce H+, and that H+ is immediately going to be grabbed up by an H2O molecule that's just floating around all over the place. So that's going to result in H3O+ forming, our hydronium, which is what we mean when we say H+ in aqueous solution. And we'll also have our chloride ion floating around. Bless you. So this is a more clear account of what's happening when we dissolve our HCl in water. Because what's actually happening is that H+ is going onto a water molecule. It also works well for some bases that don't contain OH minus ions. So ammonia, which was on that bottom entry of our table, I believe, that we kind of breezed past. Ammonia acts as a base. You can see from the formula, there's no OHs there. There's plenty of hydrogens, but we don't have any oxygens. So it can't produce OH minus ions or hydroxide ions in solution. But it works as a Bronsted-Lowry base because it can accept one of these hydrogens from water, and indirectly it forms OH minus. So since it accepts that proton, that H plus from water, that makes it a Bronsted-Lowry base. In our Bronsted-Lowry definitions, we've got proton donors and proton acceptors. And if you were not furiously scribbling things down as we were going and maybe paying attention to what our other part of our equations were, you might have noticed in one case H2O was acting as a proton acceptor. In our first example, it accepted a proton, or an H, from our HCl. In our second example, it donated a proton to our ammonia, our NH3. So water can act as both an acid and a base, and we call that amphoteric. Water is not the only one that can do it, but that's our kind of poster child for an amphoteric substance. If we flip one of our equations, like the one that we had for ammonia, earlier we saw this going the other way. We had the ammonia represented as one of our reactants and water also represented as a reactant. If we switch sides, this one works both ways. And we would think of our ammonium, our NH4 plus, as now a proton donor, and our OH minus as the proton acceptor. So we can transfer that extra H plus that our ammonia picked up earlier. We can transfer that back to the OH minus to reform water. And so in this case, since NH4 plus, our ammonium, is giving away that H plus, it's acting as an acid. The OH minus is acting as a base. And we would call ammonium and ammonia a conjugate acid-base pair. Our ammonium, our NH4 plus, is the acid, and we saw earlier that our ammonia is a base. They differ from each other by the transfer of a proton. So all that's different is that one has the extra H plus. So the base can pick up the H plus to become the acid. The acid can lose the H plus to go back to the base in a solution that's probably happening constantly. Here's that definition for a conjugate acid-base pair again. any two substances related by the transfer of a proton. So one of the acids that we saw on that table previously was sulfuric acid, H2SO4. That can lose one of these front hydrogens to become HSO4 minus, which could go back, probably wouldn't go back, but it could go back to H2SO4. So we could call those an acid-base pair, conjugate acid-base pair. We can also see it with these examples. Now we've got some pictures. So a base, like the ammonia that we saw earlier, can pick up an H plus to become a conjugate acid. The acid, in this case water, can donate H plus to become the conjugate base. For some reason, it took me my brain didn't like conjugate acid-base pairs, and so it took me a while to figure out that one of them's an acid, one of them's a base. The conjugate part just means that they're related to each other. So there's always one acid, one base in a conjugate acid-base pair. It might feel obvious, but maybe somebody needed to hear it. All right, some practice with conjugate acid-base pairs. In each of these reactions, identify the Bronsted-Lowry acid, the Bronsted-Lowry base, the conjugate acid, and the conjugate base. All right, first one. We've got H, C2H3O2. We also have H2O as our reactants. Those go to form H3O plus, and this thing, C2H3O2. The key for identifying in a given reaction, the key to identifying our conjugate acid and our conjugate base, pick two things that look similar. So in this case, we've got this thing with this C2H3O2 chunk in it. We also see that over here, but with an H with a minus. And the H is missing. Where'd the H go? The H went to the water. So what would we call this HC2H3O2? Is it an acid, a base, a conjugate acid, or a conjugate base? It's an acid. It donated a proton. And when you donate something, it has to go somewhere. Goodwill, Salvation Army, the trash can, your neighbor. Where did that proton go? It went to the H2O. And since that accepted that H plus, we call that a base. Now we have to pick out the conjugates. In a conjugate acid-base pair, acid's mentioned once, base is mentioned once. So we're pairing up an acid and a base. The conjugate part means that they're related. So H3O plus is related to the first one or the second one? The second one. And the second one is H2O, and here it's acting as a base. H3O plus then is an acid. It's our conjugate acid, because these two things are related, H2O and H3O plus. And our acid is related to this hunk, C2H3O2 minus. So that's got the conjugate label on it. And is it an acid or a base? It is a base. We've paired up our acid and our conjugate base, and our base and our conjugate acid. In B, which of the four chemicals is our conjugate base? Is it 1, 2, 3, or 4? Conjugate base.
1.
It is not 1. It is 4. 4 is the conjugate base. The conjugate part is on the right side. And it's a base. It's OH minus. OH minus is always going to be a base. Which one is our base? No conjugate.
1.
Yeah, this time it's 1. 1 is our base. How do we know? There's a couple of ways that we can figure it out. It's not an acid because there's not an H in front. So it's not going to act as an acid, not in this class. We could also look at the product side, and we see that it's picked up an H. So it went from NH2 to NH3 plus. It means it picked up an H plus. So it must have accepted H+, and accepting H+, or accepting a proton, is our definition for a base. So to get there, it must have done a base action, so it's a base. The two that we have left are our acid and our conjugate acid. Here, our acid is water. It donated H+ to methylamine, I think is what that's called. And so 3 is our conjugate acid. Questions? Confusion? Great. So that's what to know about acids and bases. Our two definitions, Arrhenius and Bronsted-Lowry, you should know both definition sets. We can do reactions with acids and bases. Our big one for acids and bases is neutralization reactions. Acid-base reactions generally form water and a salt. Sometimes it is what we call salt. Oftentimes it's just an ionic compound. This isn't always true. There are some cases where we don't form an ionic compound, but generally our acid-base reactions do this. So for example, in the reaction with HCl, hydrochloric acid, and sodium hydroxide, are acid and base respectively, the H and the OH go to form H2O, water. The Cl and the Na plus go to form NaCl. In this case, that's salt. It's also a salt, an ionic compound. If we remove the spectator ions is the salt part. We can tell because it's got AQ after it. That means it's still dissolved. If we remove that part, we're left with H plus OH minus goes to H2O. And that's the meat and potatoes, the important part of our acid-base neutralization reactions. Trying to think of a better way of saying that other than H plus and OH minus cancel out. If you neutralize an acid solution with a base or a base solution with an acid, that means that you've got equal amounts of H plus and OH minus. And that can be helpful for balancing some acid-base neutralization reactions. It's not necessary, but it can be helpful. I'll try to do an example of that if we come to something that works for that. Another reaction that often happens with acids and bases is the reaction with carbonates or bicarbonates. So things with CO3 2- or HCO3- that produce water, gaseous carbon dioxide, and a salt, an ionic compound. Like this one that I did in my backyard. I put a bunch of baking soda in this beaker that I have and poured vinegar into it. Had my phone on a little tripod, put it in slow-mo, and then picked out the best frame that I thought worked for a good picture.
You ever make a volcano? Paper machine?
I might have done the baking soda volcano once. I'm not real big into arts and crafts, though. Not paper mache, at least. It's cool, it's just not my thing. This kind of reaction is also called a gas evolution reaction, which is just a gas producing reaction. That's what the evolution part here means. The gas that we're forming is the CO2. If you're cooking and you've got an acidic component in whatever it is that you're baking, because it's really in baking, you might use sodium bicarbonate or baking soda in your reaction, in your recipe. It produces or can produce CO2 gas, and that acts as a leavening agent instead of yeast producing a gas. You can also use baking powder, which is a different thing, if you don't have an acid component in what you're baking, and that will produce that leavening action, or it'll produce this CO2 by itself. If you forget to add baking soda to a baking recipe, chances are you'll end up with a really flat, dense cake or cookies or whatever. I'm chuckling to myself about the demographics of people that were nodding their heads with me about that. Okay, write a molecular equation for the reaction that occurs between aqueous H2CO3 and aqueous NaOH. H2CO3, carbonic acid, is a diprotic acid. See if you can set up the left side, the reactant side of this equation. The two things that go on the reactant side are the H2CO3 and the NaOH. What part of H2CO3 is going to produce or make it an acid? It's the H. How many H's does it have? So if that dissolves in water, how many H pluses would we expect for each H2CO3? If we broke it down, this would be 2 H pluses and 1 CO3 2 minus. Our NaOH is going to produce how many sodiums, how many hydroxides? One Na plus, one OH minus. What's our meat and potatoes? What's the important part of a neutralization reaction? Does anyone remember? What's neutralizing what? Sort of, yes. What makes an acid an acid?
Hydrogen.
The H. What makes a base a base?
Hydroxide.
The hydroxide. These are the two things that are going to neutralize each other. That's the neutralization part of acid-base neutralization. In order for us to form H2O, we need one H plus for every OH minus. So even if we don't do the other side, do we have an equal amount of OH minus and H plus? We do not. We need more of which one? More of the OH minus. If we put a 2 in front of our NaOH, that'll balance things out. So that would be a way that you could balance it without caring about the product side. Oftentimes we don't really care about the product side. But let's say we do care about the product side, because we do here. So it's an acid-base neutralization reaction. We're going to produce H2O. And what's the other part that we're going to produce?
A salt. So it would be NaCO3.
Yeah, it's going to be a salt. The charge on Na is plus. The charge on CO3 is 2 minus. We get to crisscross them. So it's Na2CO3. When we go to balance those, the 2 NAs on the product side will match up with the 2 from the 2 that we put here earlier. You can also get this 2 that way. And since we've got 2 H's, 2 OH's, that means we'll also need 2 H2O's. Sorry if that was confusing. Kind of showed you 2 ways at once. So that's probably what I would expect you to get for this reaction. Questions? Yes?
So the 2 minus would not be there anymore when we're actually writing it out, right? It would just go directly underneath the NA.
Correct. The plus and the 2 minus were just there to illustrate how we got the 2. In reality, this would probably be a gas evolution reaction since we've got the CO3. This H2CO3 is how carbon dioxide is like in carbonated beverages. That's how it exists when it's dissolved. And then it produces CO2. Okay, other reactions that we can do with acids and bases. With acids, we've got some important ones. Acids can dissolve many metals, many but not all metals. So things like zinc and magnesium will dissolve in hydrochloric acid. And it forms hydrogen gas. H2. And it also forms a salt that has the metal in it. We did this second one. If you remember when we had the UDiometers, we flipped them over and we had the little magnesium strip that was dissolving. Some metals don't react readily with acids. the fancier metals, things like gold, silver, platinum. That's part of the reason that they're used for fancy jewelry, is because they don't react with things very much. So that's one of our two important reactions. Here's a picture we saw earlier. This is zinc metal dissolving in HCl. This reaction typically produces hydrogen gas. Again, that's the H2. And the dissolved salt that has the metal, in this case, zinc chloride. It's dissolved because it's got the AQ behind it. Another reaction that we can do is reacting acids with metal oxides. So this is very, very similar. Almost identical to the reaction of acids and metals. When we had acids and metals, the magnesium, for example, reacted and it formed H2. We've added this oxygen. That oxygen goes with the H2 now. And so it forms water instead of H2 gas. So you remember for that eudiometer lab, the gas one, the hydrogen gas one, had you sand down the piece of magnesium, just the surface? That's because the surface reacts with oxygen in the air and it forms this metal oxide. So if you react metal oxide, we're not producing hydrogen gas, we're producing water, and that wouldn't show up in our reaction. So we would be producing water instead of H2. So to get a better yield, we scratch off the metal oxide, the MgO, so that we're not producing water. Everything that we're putting in there is going to produce H2 gas, or at least that's the idea. So there's another thing to know. All right, now you get to try writing some equations. See if you remember your nomenclature. Write out the reaction of hydroiodic acid with calcium metal and the reaction of hydrochloric acid with magnesium oxide. What is hydroiodic acid? HI. The hydro part means it's a binary acid. Iodic is the base plus ic for iodine, so it's HI. And that's reacting with calcium metal. When an acid reacts with a metal, it produces what? Hydrogen gas, H2. It also produces a salt that has the metal in it. Calcium is a 2+ when it forms an ion. Iodine is a 1- when it forms an iodide. So we'll need CaI2. So we'd put a coefficient of 2 in front of our HI. In B, we have the reaction of hydrochloric acid, again with the hydro in front. So it's HCl, a binary acid. And we're reacting that with magnesium oxide. Magnesium forms a 2+ as an ion. Oxide is a 2-. Those are a 1-to-1, so it's just MgO. So the difference is now we have the oxide. That oxide goes with the H2. So we have H2, and the oxygen goes there too. H2O, that's water. And we also have our salt featuring the metal from the metal oxide. And again, we need a coefficient of 2 in front of our HCl to balance it. Questions about those? Cool. There are some base reactions. The most important one is the acid-base neutralization reaction. The other one that is worth mentioning is dissolving aluminum. You may remember from Lab 8 that aluminum dissolves in base. I don't remember if we used sodium hydroxide. I think we used potassium hydroxide. It dissolves aluminum metal. We did that outside. We got to do chemistry outside. And dissolve that in base. There's the whole balanced equation. I don't think it's particularly noteworthy, so it probably won't show up on an exam. But the part that you should definitely know is that aluminum dissolves in base. That should be the takeaway. Within the realm of acids and bases, there are two ways that we can describe them, either as strong or weak acids and bases. We won't go into the extent of weakness. Strong is kind of just like it's strong or it's not strong. So hydrochloric acid, HCl, and HF look very similar. It's a binary acid. It's got one H, and it's got a halogen, either chlorine or fluorine. They're different though. HCl is a strong acid. It completely ionizes in solution. HF, on the other hand, is a weak acid. It does not completely ionize in solution. I think we talked about strong and weak electrolytes last chapter. Same idea here. So if it's strong, completely dissolves. If it's weak, does not completely dissolve. Strong acids, like HCl, ionize completely there are no HCl units in solution. They all got broken apart. If we have a 1 molar HCl solution, that will have a concentration of H3O plus that's equal to 1 molar. It's a 1-to-1 ratio, that's why they're the same. The brackets around the symbol, this part, means molar concentration of. There are a lot of strong acids. The ones that are bolded here, I'll also put an arrow pointing at them. These are the ones that you should know are strong acids. So hydrochloric acid, which we've talked about a bit, nitric acid, we've used before in lab, and sulfuric acid. Most of these are monoprotic acids, meaning that they just have one H in front. Sulfuric acid is diprotic. Two H pluses can be formed. There's also things like phosphoric acid, H3PO4. Any ideas what we would call that? Triprotic. So you can pull off all three of those H's that live up in front in solution. So those are some strong acids. We also have weak acids. Weak acids are ones that don't completely ionize. And so you will find fully intact units in solution. In this case, HF. And we can see in our very high-tech diagram, we've got HF floating around in there with our H pluses and our F minuses. There's a balance between the amount of H3O plus and F minus with the HF. So there will always be a little bit formed, but there will also be some of the HF present. A key indicator here that this is, if you weren't just told that it's a weak acid, this double arrow means that it's a weak acid. So this means that the reaction goes both ways. The HF can dissociate to become the H3O plus and the F minus. These can also go backwards to reform the HF. The KHP that we used last week in lab, that's a weak acid. The solid acid that we're going to be using today and Thursday, also a weak acid. We're using a weak acid today and Thursday. Here are some weak acids. There's two that you should know for this class. hydrofluoric acid, and acetic acid. There's lots and lots and lots and lots of weak acids. Most carboxylic acids, those are the ones that have this CHO thing, like N-acetic acid and formic acid. That's an indication that it's a carboxylic acid. We also have here an important caveat about sulfuric acid. So sulfuric acid was listed with the strong acids. And that's true, it is a strong acid. H2SO4 is a strong acid that would go to produce an H plus and HSO4 minus. HSO4 minus is a weak acid. So for sulfuric acid, the first one's strong, the second one is weak. And I'm mentioning that specifically for a reason. Sometimes it's obvious, but sometimes it's just worth mentioning that it's intentional. You can imagine me bumping you with my elbow on that one. Or like raising my eyebrows. Okay, we can also determine either exactly or vaguely the H3O plus hydronium concentration of different solutions of acids. The key for doing these types of problems is identifying, is the acid strong or weak? HC2H3O2, acetic acid, is that strong or weak? Any ideas?
Weak.
It is weak. So we've got a weak acid. What does that mean that it's a weak acid?
Is that it partially dissolves in solution?
It partially dissolves. If it completely dissolved, what would be the acid concentration, or what would be the H plus concentration? It doesn't. If it did, let's say, how many H's here can go to produce H3O plus? Pick a number between 0 and 4.
3.
It's not 3. Pick a different number between 0 and 4. It's also not 4. It's not 2.
It's 1.
It is 1. How do we know it's 1?
It's in the front.
We have one H in the front. I'll do that in blue since it's not related to it being a weak acid. One H in front can produce one H plus in solution, a maximum of one H plus in solution. If it was a strong acid, that means that every single one of these units would break apart into H plus, and acetate is the anion. That means that our concentration would be the same. So if it was strong, that concentration would be 0.80 molar. It is not strong. Are we going to have that amount of H plus, more than that amount of H plus, or less than that amount of H plus? It's less. I feel like I'm just confusing people. So it's weak, which means that not all of that will break up to form H+. So the concentration of H3O+ will be less than. I'm going to draw arrows because if I underline it, that means a different thing. Will be less than 0.80 molar. Let's say that I have $50, which is true. I do have $50, just not on me. It's hidden somewhere. It goes to a different school. So my $50, right? A couple of us are going out to get lunch, and I'm paying for some reason. So I've got $50. A couple of people are going to lunch. I'm paying. How much money? Wait. Processing. Let's say that Jesus and I are going out to lunch, and I'm paying. I've got $50. How much money does Jesus have to spend on lunch if we're splitting it evenly? $25, right? Because I'm not giving him the money saying, hey, here, go buy food. That would be like the weak acid case. It's not all going to Jesus. If, however, Jesus crushes it, he's my top student, and I say, here's $50, go have lunch. How much money does he have to spend on lunch? $50, because he's getting the whole thing. For some reason, my brain thought that was a good example for strong versus weak. Anyway, the takeaway is we've got a weak acid. It's not all dissociating. It's going to be less than this concentration of acid. It's not all of it is getting paid out to H+. Yeah.
So if he did good, which is he did strong in class, then he took it all, so he would take the full amount.
That works.
So if he didn't do well, he was weak in class, so he didn't take the full amount.
That also works. Sure.
I understood that more than the first
Those examples help, so I'm trying to connect.
Yes, those ideas connect. Okay, HNO3, nitric acid, is that strong or weak? It's strong. What does that mean about the amount of H+ that it forms? Does it all form H+? Does some of it form H+? Does none of it form H+? All of it forms H+. And we've got one H in front. So every one of these HNO3s is going to form H+. So our concentration of H3O+ is equal to that concentration. Maybe a better example would be a parent incentivizing their student, or their kid rather, to do well in class. If you get an A, I'll give you $50. If you get a B, I'll give you 75% of that. Something like that. Maybe that would be a better example.
It's a work in progress.
Yeah. We can't all be perfect on the fly. We being me. All right. HF, strong or weak? Weak. We saw earlier what happens for weak acids. So what's our concentration going to be here? Less than 0.70 molar. One final secret, super important example, possibly. What if we have 1.5 molar sulfuric acid? There's a fun little trick about sulfuric acid. What is it?
Hydrogen in it? The amount of hydrogen?
There's 2 hydrogens. That's important. It showed up on both of our lists, or related to both of our strong acid and weak acid lists. So for H2SO4, the first is strong, and the second is also strong or weak? It's weak. So when that first one pops off, what is our concentration at that point? The second one's weak. So we've already got this 1.5 because this first hydrogen popped off. Now we just have 1 H left. The second one is weak. What does that add to this 1.5? Does it add some, all, none? Some. So we're going to have at least 1.5 molar. But it's not going to be all the way up to 3, which would be twice the amount. If they were both strong, then it would be 3. Questions about any of that? Okay, we will pick up with strong bases next class. We'll also be talking about logarithms. You don't need to know how logarithms work, but I will talk about it.